In this unit, learners will become familiar with key subjects in mathematics that are of use in the field of computer science. The unit begins with an introduction to binary numbers, which form the basis of the representation of information in computers. Learners will then be taught key principles in the fields of Boolean propositional logic and set theory, including Boolean operators, and will be given an introduction to proof techniques in mathematics. Number theory, linear algebra, and sequences and series are also covered to equip learners with a mathematical toolset that will enable them to reason about problems in computing. Bases and representation include base 16, base 10, and base 2. These numeral systems are fundamental to how humans and machines represent and process numbers. Base 10 decimal is the most familiar, used in everyday arithmetic. Base 2, binary, is the foundation of digital systems, while base 16, hexadecimal, is often used in computing as a compact way to represent binary values. Historical reasons for bases and their representation are explored. Early civilizations used various base systems like base 60 in Babylonian mathematics or base 20 by the Mayans, often influenced by counting tools like fingers or cultural factors. In computing, binary and hexadecimal were adopted for their simplicity in implementation and readability in low-level programming. Binary in computer science is discussed with emphasis on its resilience to noise and error in storage media. Binary signals comprising only 0s and 1s are less prone to degradation, making them reliable for data transmission and storage. Devices can distinguish between two voltage levels more easily than multiple levels, which increases accuracy and fault tolerance. Understanding the representation of numbers in binary, including floating-point representations like the mantissa and exponent. And 2's complement is essential. 2's complement allows efficient representation of signed integers and simplifies arithmetic operations in hardware. Floating-point representation, IEEE 754 standard, enables the storage of very large or very small numbers using scientific notation. Where the mantissa stores significant digits and the exponent indicates scale, connections to Boolean logic and Boolean set operations are also highlighted. Binary values align naturally with Boolean algebra, which underpins logic gates and decision-making in digital circuits. Operations like AND, OR, NOT XOR are used in everything from arithmetic operations to conditional logic and programming. A number system defines how we represent numbers using a base or radix. The most common bases are binary, base 2, octal, base 8, decimal, base 10, and hexadecimal, base 16. Binary uses only 2 digits, 0 and 1, with each digit representing a power of 2, increasing from right to left. An example is converting binary 1011 to decimal, which equals 11. Converting between bases involves understanding how each digit represents a different power of the base. To convert decimal to binary, divide the number by 2, record the remainder, and repeat with the quotient until it's 0, then read the remainders in reverse. For binary to decimal, multiply each bit by 2 raised to its position and sum them. Decimal to octal involves grouping binary digits in sets of 3, while decimal to hexadecimal uses sets of 4. Understanding base conversions is essential for programming, networking, and hardware design. Binary representation refers to expressing numbers, data, or instructions using only 2 digits, 0 and 1. This system is known as the binary number system or base 2, where each digit is called a bit. The binary system uses powers of 2, and binary numbers are positional, meaning the value of each bit depends on its position. Digital computers use binary because electronic circuits have 2 stable states, on and off. All data in computers is ultimately stored and processed in binary. Digital computers use binary because electronic circuits only have 2 stable states, on and off. Binary is reliable, fast, and easy to implement in hardware using transistors. All data in computers' text, images, sound, video is ultimately stored and processed in binary. For example, the letter A in ASCII is represented as 01000001. Binary representation is the foundation of computing, allowing complex operations to be performed using simple Two-state logic. To convert decimal to binary, use repeated division by 2 and record the remainders. Divide the decimal number by 2, record the remainder, and continue dividing the quotient by 2 until it becomes 0. Read the remainders from bottom to top to get the binary equivalent. For example, converting 18 to binary results in 10010. This method helps in understanding how numbers are structured in binary form. To convert binary to decimal, multiply each bit by 2 raised to the power of its position and then sum the results. Label each bit with its position from right to left starting with 0. Multiply each bit by 2 raised to its position and add all values. For example, converting 1011 to decimal results in 11. This method is crucial in understanding binary number structures. To convert binary to hexadecimal, group binary digits into 4-bit groups from the right and convert each to a hex digit. For example, converting 110101110 to hexadecimal involves grouping as 11010110, resulting in D6. Each group of 4 binary digits corresponds to 1 hexadecimal digit. This conversion is useful in programming and digital electronics. Understanding this helps in dealing with large binary numbers efficiently. To convert hexadecimal to binary, convert each hex digit to its 4-bit binary equivalent. For example, converting 9F to binary involves converting 9 to 1001 and F to 1111, resulting in 100111111. This conversion is essential for understanding how hexadecimal numbers are structured. It simplifies working with binary numbers in computing. Hexadecimal is often used as a shorthand for binary in programming. To convert decimal to hexadecimal, use repeated division by 16, tracking remainders. For example, converting 255 to hexadecimal involves dividing by 16, resulting in FF. This conversion is crucial in computer programming and digital electronics. Hexadecimal provides a more compact representation of binary numbers. Understanding this conversion aids in efficient data representation. To convert hexadecimal to decimal, multiply each hex digit by 16 raised to the power of its position and sum the results. For example, converting 2a to decimal involves multiplying 2 by 16 and a by 1, resulting in 42. This conversion is important in understanding data representation in computing. Hexadecimal numbers are widely used in programming for their compactness. Mastering this conversion is vital for efficient programming. Numbers are represented in binary using only 2 digits, 0 and 1, known as the binary number system or base 2. Each digit is a bit, and its position determines its value based on powers of 2. This positional notation means each bit represents an increasing power of 2. Binary numbers are foundational to digital electronics and computing systems. Understanding binary representation is key to grasping how computers process data. To represent the decimal number 13 in binary, find the highest power of 2 less than or equal to 13. Subtract and continue with the next highest power of 2 until reaching 0. For 13, this results in 1101 in binary. This example illustrates the process of binary conversion. It highlights the importance of understanding powers of 2 in binary representation. Binary representation in computing includes unsigned binary, signed binary, 2's complement, fixed point, and floating point binary. Unsigned binary represents only positive integers. Signed binary is used for negative numbers, with 2's complement being the standard. Fixed point and floating point binary represent fractions and real numbers. Binary coded decimal, BCD, represents each decimal digit with its own 4-bit binary value. Binary is used in computers for its reliability, efficiency, and universality. It operates with only 2 states, on and off, easily detected electronically. Binary allows for simple circuits and fast processing. All data types can be reduced to binary, making it a universal language for computing. This universality is why binary is foundational in digital electronics. Binary representation offers simplicity and reliability in hardware due to its two distinct states, on and off. It enables efficient processing with modern processors optimized for high-speed binary operations. Binary is versatile, representing all forms of digital data through encoding schemes. It supports robust error detection and correction techniques. Compatibility with Boolean logic simplifies algorithm and circuit design. Binary numbers are difficult for humans to read directly, leading to the use of higher-level representations like hexadecimal. Binary requires more digits than decimal, which can increase memory usage. Representing real numbers in binary introduces complexity and potential errors. Despite these challenges, binary remains essential in programming, networking, and file storage. Its limitations are well managed by software and higher-level abstractions. In programming, binary is the language of machine code. High-level programming languages are ultimately translated into binary instructions that the CPU can execute directly. Each binary instruction corresponds to specific operations like arithmetic, data movement, or control flow. Networking relies on binary for IP addresses and subnetting. IP addresses, both IPv4 and IPv6, are represented in binary at the hardware level. Subnetting involves binary division of address spaces to efficiently route and manage network traffic. File storage involves binary sequences for data representation. Whether it's text, images, audio, or video, all file types are ultimately encoded in binary. File formats define how binary data is structured and interpreted by applications and hardware. Embedded systems, like microcontrollers, operate entirely on binary logic. These systems use binary instructions to control hardware components, respond to inputs, and manage tasks with real-time precision. Their compact, efficient operation depends on direct manipulation of binary values. These applications highlight the integral role of binary in modern technology. From software and networking to storage and hardware, binary underpins how digital systems operate and communicate. Understanding binary is crucial for anyone in the field of computer science. It lays the foundation for learning programming, system architecture, hardware interaction, and low-level problem solving. In conclusion, binary representation is the bedrock of digital computing. It forms the foundation of how computers store, process, and transmit information, using only two states, 0 and 1, to represent all forms of data and instructions. It offers unmatched efficiency, reliability, and compatibility with electronic hardware. Binary aligns seamlessly with the on-off states of transistors in digital circuits, enabling fast, consistent, and error-resistant data processing. Its simplicity also facilitates straightforward hardware implementation. While it is not human-friendly and may result in lengthy representations, especially for complex data or large values, these challenges are not obstacles to effective computing. These limitations are efficiently handled by software layers and higher-level abstractions. Tools such as compilers, interpreters, operating systems, and user interfaces bridge the gap between human logic and machine language, making development and interaction intuitive and accessible. Thank you for watching the video.